Hey, and welcome. Have you ever just looked around you? I mean, really looked. Your phone, that chair, the room you're in, it's all made of something. And for an engineer, knowing the secrets of that something is, well, it's the whole game. So today, we're going to peek behind the curtain and see the world just like they do. So let's kick things off with a question that sounds simple but is actually kind of profound. Why can you bend a paperclip into all sorts of shapes, but if you try to do the same thing with, say, a glass rod, snap? I mean, they're both solid, right? Well, the answer is hiding inside the materials themselves, and that's exactly what we're here to unpack. All right, so imagine you're an engineer. You've got this massive project, maybe a bridge. You have to pick the perfect material. But how do you even begin to compare them? You can't just say this one feels strong. You need a shared language, a way to describe exactly how this stuff behaves. And that language, it's all about properties. And look, these properties aren't just some random, messy list. They're actually sorted into these neat little families. You've got your physical properties, like how heavy something is for its size, that's density. Then you have chemical, thermal, electrical, but for us, the real rock stars today are the mechanical properties. These are the ones that tell an engineer how material is going to react when you push it, pull it, or twist it. Just to make this real, let's take a quick peek at the thermal family. This table shows thermal conductivity, which is just a fancy way of saying how fast does it get hot. And whoa, the differences are absolutely massive. If we say silver is our standard, a perfect 100, look way down at the bottom. Cork is just 0.01. This one little number explains something you see every day. Why the metal pot on your stove gets screaming hot, but the wooden spoon you're stirring with stays cool enough to hold. It's all about conductivity. Okay, let's zoom in on those mechanical properties now. Because when you're building something that absolutely cannot fail, think a skyscraper, a jet engine, these are the properties on every single engineer's checklist. They're the crystal ball that predicts if a material is going to bend or break or just hold its ground under incredible pressure. Now here's a classic mix-up. Strength versus stiffness. They sound like they could be twins, right? But they're totally different. Strength is just about the raw, brute force a material can take before it fails. Like, how much weight can this hold? But stiffness, that's all about resisting bending. A steel beam is ridiculously stiff. It barely sags. Now, an aluminum beam of the exact same size, it might be strong enough not to break, but it's going to bend and sag a whole lot more. That difference is absolutely critical. Next up, elasticity. And the perfect picture for this is just a rubber band. You stretch it, you let go, and snap. It zips right back to its original shape. That's elasticity. But it's not just for rubber bands. It's happening on a huge scale in something like a bridge. It's designed to flex a little with wind and traffic and then bounce right back perfectly, preventing any permanent damage. So what happens when you stretch something so far that it doesn't bounce back? Well, that's called plasticity. It's the ability for a material to permanently change its shape without breaking. Think about squishing a piece of modeling clay. This property is, frankly, the magic behind manufacturing. It's what lets us take a boring block of metal and stamp it into a car door or forge it into the complex parts of an engine. And plasticity itself actually splits into two different skills, which you can see here. On one side, you have malleability. That's the ability to be hammered or rolled into super thin sheets. Picture a blacksmith at an anvil. Then on the other side, you have ductility. That's the ability to be drawn out into a thin wire. It's exactly why all our electrical wires are made from copper, because it's so ductile. And here's the key. They are not the same thing. Lead, for example, is incredibly malleable. You can flatten it out all day. But try to pull it into a wire, it'll just snap. Okay, so we've got our language of properties down. Now we can start organizing the massive library of materials that engineers get to play with. And the very first, most basic split is a big one. You basically divide everything in the world into two huge families, metals and nonmetals. And as this slide shows, the differences are truly night and day. Metals, they're usually shiny, they're fantastic at conducting heat and electricity, and as we just learned, they're often malleable and ductile. Nonmetals are, well, pretty much the polar opposite. They're typically dull, they act as insulators, and if they're solid, they tend to be brittle. Just picture a shiny, flexible copper wire versus a dull, crumbly piece of sulfur. It's a perfect contrast, right? All right, let's go exploring in the metals section of our library first. And we absolutely have to start with the undisputed heavyweight champion of engineering materials, the ferrous metals. Ferrous is really just a fancy word for anything that's based on iron. What's just incredible about iron is how you can completely change its personality just by adding a tiny pinch of carbon. Seriously, a little bit gets you mild steel, great for building frames. Add a bit more, and suddenly you've got this super hard, high carbon steel you can use for knives and tools. And if you add even more, you get cast iron. It's brittle, yeah, but it's fantastic for casting into really complex shapes, like an engine block, all from a little bit of carbon. But adding carbon is just the start of the fun. This is where it really gets to be like cooking a recipe. You start with your basic carbon steel, right? Then you start adding other ingredients, what we call alloying elements, to give it superpowers. Want it to fight off rust? Add some chromium, and boom, you've got stainless steel. Need it to stay hard even when it's glowing red hot? Add a dash of tungsten, and now you have a high-speed tool steel. It's all about the recipe. Of course, there's a whole world of incredible metals that aren't based on iron. These are the non-ferrous all-stars, and as you can see, each one has its own claim to fame. Aluminum's defining feature? It's crazy lightweight, which is exactly why we build airplanes out of it. Copper is the absolute king of electrical conductivity, no contest. And zinc is so darn good at resisting corrosion that we literally wrap steel in it. That's called galvanizing. Okay, time to leave the metals behind. Let's cross the aisle in our library over to the non-metals. And trust me, this side is just as huge and just as important. It covers everything from modern cutting-edge plastics to ancient materials we still use every single day, like wood and glass. Now, inside the world of plastics, there are two major families, and what separates them is how they deal with heat. First, you have thermosetting plastics. Think of these as a one-and-done deal. You heat them up, you mold them, a chemical change happens, and that's it. You can never remelt or reshape them. But thermoplastics, they're different. You can heat them up, soften them, and remold them again and again. That's what makes them so great for recycling. But here's the thing. Whether they're thermosetting or thermoplastic, all plastics share some amazing superpowers. They are incredible electrical insulators, which is why your cables are wrapped in plastic. They have a fantastic strength-to-weight ratio, and they are unbelievably resistant to corrosion from chemicals, oils, you name it. This mix of properties is what makes them useful in, well, almost everything. And finally, let's not forget the OGs of the non-metal world, the natural materials. I mean, we've been using these for thousands of years, and they are still absolutely essential. We use wood for its workability, glass for its transparency, rubber for that amazing, unique elasticity, and of course, diamond for being the hardest thing around, perfect for cutting tools. Every single one is still a vital part of a modern engineer's toolkit. You know, this quote really just nails the whole point perfectly. Building amazing things isn't about finding one single best material that solves everything. It's about knowing, really knowing the unique personality of all the materials in your toolkit so you can pick the absolute perfect one for the job at hand. And that brings us right back to where we started, with our paperclip and our glass rod. One has plasticity, the other is brittle. And understanding that simple, fundamental difference in their properties is how we built the entire modern world, from skyscrapers to spacecraft. We've pretty much mastered steel and plastic. But you know what? The search for new materials never ever stops, which leaves us with a really exciting final thought. What will the next super material allow us to build? Thanks for joining us.